No, so we are now recording the meeting for the intro exam. If you have any questions, you're welcome to shout them out, or if you want to type any questions, that's fine too. First question up, how many questions are on the exam? Okay, answered for you. 15 questions total, 10 multiple choice, 5 true, false. The unit exams are going to be a little bit bigger than that. It's 25 questions, all multiple choice. And then that'll be the format for the exams for the rest of the semester. This one's just a little more slit of an exam. Another thing I'm going to do is go ahead and start doing a share screen deal. What we're going to mainly do is go over the review questions that just pertain to the first 2 lectures that are actually going to be on the exam for Tuesday. At any given time, you're very welcome to ask questions, give comments verbally or in text. Let me concentrate on what I'm doing here. Share screen, entire screen. There we go. So I'm only briefly going to be back on the screen. If you type a question in at any point today and I don't get to you right away, we'll kind of come back to the screen occasionally and check if there are any questions. But I'm basically just going to be going over exam format, instructions, and mostly just a review of actual content. Screens are optional. You guys can keep your cameras off or turn them on, whatever makes you more comfortable. I'm not fussy about that. So please also kind of give me an indication if you're not seeing anything, or if it's not visible, and I can try to do some fixing. But I think we should have everything pretty much set up. So I'm going to go into Moodle, kind of show you where you can access all of this information. I'd like to think it's pretty straightforward, and I try to make it relatively user-friendly. But as you go into the course, you can go into Unit 1, Tectonics, and you have, of course, the links for the individual lectures, the outlines. And I've mentioned this earlier in the class overview, but those outlines actually work as a better study guide, like a more sort of comprehensive list of all of the stuff that I go over in the lectures. They work better as an actual study guide than the review questions do. The review questions aren't meant to be comprehensive. They're meant to sort of target these things that are hard to understand in the lectures. So it's not going to be like a recitation of just definitions of terms. It's more, tying a whole bunch of thoughts and ideas together in those review questions. And so that's, how I usually like to do reviews, because then you're definitely sort of on the right track. You can do these review questions ahead of time if you want, use this to check, or just go through them with me, however you want to do that. So the lecture link itself, the outline works more as a study guide, and then the individual quizzes that closed last week. So the stuff that we've done so far was lectures 1 and 2, plate tectonics and geologic structures. Plate tectonics should be relatively simple, and I doubt it's the first time you've heard at least some of the general concepts there. We will be going over some of the information from that lecture, but I would think that if any of it's going to give you a bit of a hard time, it's going to be some of that stuff with geologic structures. A lot of people will do other topics first in geology, like cover rocks and minerals first, and especially sedimentary rocks, to give you a little bit more of a basis for geologic structures. But I like to do this whole unit on tectonics first, sort of set a framework for all the chemistry that we're going to do later. So the geologic structures lecture is, a little bit more daunting, and we'll spend quite a bit of time on that today. Before I forget to mention this, as far as stuff that is accessible to study that might be a good idea, you can go back and review these review questions. Review the quizzes, and then use those as sort of additional review questions. Particularly if you didn't get 100% on those. For one, it's not a big deal because they're not worth that many points. And then 2, you can go back and you can now see what you did wrong, because once the quiz is closed, the correct answers appear. So that's lectures 1 and 2. And then there's all the stuff down here for the intro exam. This is where I'm going to put this recording today. I'll just stick it in as an extra topic here. And then you have the actual exam itself, the review questions that we're going to go over, and then this lockdown browser check. If you've done a bunch of these before and you're pretty confident you've got the Respondus browser already set up on your device, on your computer, and everything's good, then you don't necessarily need to do this. But if you've never done one of these exams before, it makes it a lot easier if you set up everything in advance, because at least then you know that the tech aspect of taking the exam is already done and you can just concentrate on getting the right answers. So we're going to, well, I might as well just do this real quick. As you go into the actual exam itself, it's going to be closed right now, but it doesn't let you open it without setting up the browser first. It's not going to open until 6 p.m. tomorrow, and then it'll close 24 hours later. Now, there was a little bit of chatter either on the group chat for this class or possibly for 102 about like, why is it 6 p.m. for everything? Why don't I have stuff due at midnight? And it's for the simple reason I like to be able to help people if they have problems at 6 p.m. And I'm dead to the world at midnight. I'm not really in the, in the right frame of mind to be able to help anybody with anything. I'm totally asleep. I've got small children. So, 6 p.m. is, when I can actually help. If you have some last minute sort of crisis, I can do something at 6 p.m. I can't really do anything about it at midnight. So that's essentially why it's 6 p.m. and not midnight, but it's still just 24 hours. So you have 6 p.m. Monday to 6 p.m. Tuesday. I would probably try to do it either Monday night or earlier in the day on Tuesday, so that if you find out like, oh no, this computer is not right for taking this exam or something else happens, then you can at least address the problem before it closes. What sort of a weird thing that I think I've mentioned everywhere, Respondus Lockdown Browser does not work on Chromebooks. It only works on PCs and Macs. So you have to be taking the exam on either a regular Windows PC or a Mac. I've even got it set up so it should work on like iPads. That should be okay, but just not Chromebooks. For whatever reason, that software is incompatible. Last thing, and I mean, I'm talking to the people in this review. I doubt this is going to really be something I need to worry about with you guys, but the whole purpose of using the Respondus Lockdown browser with the monitor is to be able to effectively just sort of be able to watch the people take the test. And 95% of the time, I don't watch your video. I only go back and access videos if the software flags some sort of suspicious behavior. Like I had somebody last semester that put a Post-it note over their webcam, and I watched them do this. So that was a 0. There's nothing, really to be done about that. Essentially, I just want to be able to make sure this is you taking the exam, not a group taking the exam, not someone else, and not you with access to the web. So that I know that you are the one that's understanding the material. So, okay, all that should be pretty straightforward, but I just wanted to go over it while we were talking about the exam. Let me hit up the Meet again and see if anybody has questions. No, we're good. So going back here, what I did already was I went ahead and opened this. It's a Word document, and I do Word documents instead of PDFs so that you can type directly into the document. But I went ahead and opened this. You're welcome to do the same if you want to do this with me, or however you want to do this. I'm going to go through and look at these review questions. So later on, we're going to have an extra credit assignment that's tied to the Unit 1 exam, and there'll be a unit extra credit assignment for each unit exam. I don't have one with this intro test because it's just 2 lectures, but in the instructions for this, I've got, one of these questions shows up as the extra credit assignment question. So essentially by, coming back and joining me for this review, you always know you're going to be getting that question right. You can effectively just sort of rephrase it and put it in your own words, make it 100 words, and you got the extra credit assignment. The questions that actually pertain to the first 2 lectures are just the first 3 questions. So it's a question on heat engines, a question on plate boundaries, 1 and 2, those are both coming from lecture 1. And then the third question is, what are the 3 types of faults? All of the rest of this is from quizzes 3 through 5, and we don't even get into, lectures 3 through 5, and we don't even get into that until the next unit. So I'm going to go ahead and just kill those real quick. And then I'm going to give myself a little bit of space. And we'll go through and talk about the answers here. Okay, let me go back to the chat real quick and make sure we're good so far. Yeah. So in this first question, describe the major mechanisms that drive geology on planet Earth. Hence, they were described as internal and external heat engines. So internal versus external. Now, this is just a thought device. Obviously, these aren't real engines. I've just always really liked this, way of kind of expressing this, because it makes it really clear that there is a source of heat in our solar system that is not the sun. It's remnant heat from the formation of the Earth and heat from radioactivity and convection and conduction. All of that, those processes are also generating their own heat. So there's internal heat for not just Earth, but many of the planets. Some of the really, really cool objects like Mercury and the Moon have cooled off long ago. They're no longer geologically active. But most of the things that we think of as actual geological activity are all related to Earth's internal heat. So that's what I'm talking about with these major mechanisms, the internal and external heat engines. This is what is the source of heat and how does that heat translate into geological activity? So the Earth's internal heat engine is remnant heat from the formation of the Earth plus radioactivity plus convection and conduction. Heat transfer, primarily convection, leads to tectonic activity and let's see, let me specify heat transfer in the mantle, primarily convection, leads to tectonic activity, and heat transfer in the core leads to magnetic field generation. Tectonics So there's this process I'm trying to convey here, and this isn't coming across real well in a paragraph form, especially with these sort of stilted sentences, but there's the heat engine, and then that heat engine is going to drive heat transfer. So there's the fact that the core of the Earth is hot, that heat is radiating outwards and it's convecting outwards, right? So the heat drives convection. Convection then drives tectonic processes. And then the tectonic processes include things like volcanic activity. I think I worded it in the notes as volcanism, so that's all the same thing. Plate motion / plate tectonics. Plate motion, plate tectonics, and just sort of the general redistribution of tectonic plates, right? And continental drift and the change in the surface of the Earth over time. It's all sort of related back to tectonics. So there are many, many different ways that you could phrase this, and you could phrase this entire concept of internal heat engine completely different, and still it would be effectively the right answer, as long as it's including something that's related to the idea that the interior of the Earth is hot, the interior of the Earth drives convection, so that's heat transfer, where hot material is rising, cold material sinking back down. That's then relating to these tectonic processes, the plate motion, plate tectonics, and then which leads to geological phenomena. That's the way I described it in the text of the question, such as earthquakes, mountain building, volcanoes,
Excuse me?
etc. Yes. Okay.
Is there going to be like a fill in the blank where we have to do any, or is it going to be just like multiple choice?
Not at all. No. Definitely. The format of the exam's 10 multiple choice, 2 true false.
That sounds so easy, yet so complicated. I'm scared.
No. I hate it. I think, I don't know why. What I find happens is, to kind of just like step away from the scary review questions too for a second and just kind of go back to the meat of these exams. What tends to happen is I get a pretty big split in how people do on these exams in the class. I have the people that actually watch the lectures, take good notes, and have a really good sort of conceptual understanding of what's going on. They may not memorize every term. The word tectonism might still kind of jar them a little bit, but they have this basic understanding of these processes, and they do relatively well on the exam.
Okay, because I went through like the lectures and I took the notes. Now I did go and look at some like the vocabulary words that were in like the textbook, but I didn't know if I was doing too much because some of the stuff was like jargon to me.
Oh yeah. Okay. Well, okay.
I was confused on what to study overall.
Finishing at the last thought, like basically, like that was like everything I was talking about before. Those are the people that do pretty well, and then there are the people that always try to just sort of like memorize their way through the material, and they try to kind of like like Quizlet study everything. Especially those who are using like a Quizlet that somebody else made, and they've never watched the lectures. And when they go, but I did that, but I didn't do very well. And it's because they didn't really have this sort of like basic understanding of concepts and processes.
Okay.
Okay. So, what was the last thing that you said? I wanted to address that.
So I went through like the textbooks for the chapters 1 and 2 for vocabulary, and I was writing them down with some of it, and some of it was just like, I think we touched on it, but it wasn't like how. It wasn't like the text. I don't know. I feel like I was doing too much going through the textbook vocabulary words.
Well, definitely with chapter 2, we don't get into that until the next unit.
So I felt like I was doing too much.
The textbook is actually, and I'm going to write this in the chat, is chapter 1 and chapter, I want to say it's 15, but I'm going to look that up real quick. I jump forward in the textbook quite a bit. Let me go back to the syllabus real quick. Unit 1, plate tectonics is chapter 1. Geologic structures is chapter 15. So chapter 2 doesn't come into it until unit 2. Just 2, 1 and 15. So specifically with the textbook use, especially with the second lecture, there's going to be a lot of things from the textbook that I don't cover as part of the lecture, and that's not fair game for the exam. So I'll never put something from the textbook that I don't also cover as part of the lecture.
Okay, so I'm not going to say not disregard the textbook per se, but just more focus on what you're saying in the lecture more, and then if I need elaboration, go to the textbook.
That's exactly how I would do it. And I would even go so far as to say that some people won't even need the textbook. I consider the textbook optional. If you not look at the lecture and you go, oh, that was all really weird to me. Like I need it explained in a different way, or I need it explained again, or, I need to clarify, just individual points. Then I would go to that stuff in the textbook. Just kind of use it as a supplemental resource. Okay, so going back to the text of these review questions. I'm probably getting a little wordy here, but essentially what I'm trying to do here is say internal versus external heat engines. This internal heat drives these internal processes, which then drives stuff that happens on the surface, like mountain building, volcanoes, trenches, earthquakes. This is like a surface expression of all of this internal heat. The external heat engine is heat from the sun, which drives weather, climate, which then leads to surface erosion, canyon formation, rivers, etc. It's probably the level of detail I should have answered this first question, and I just got a little maybe nervous and carried away. So this external heat is going to be processes in the atmosphere that affect the surface, as opposed to the internal heat engine being all of these internal heat processes that then affect the surface. Then both the internal and external heat engines are driving geology. And so that's why I kind of start the class with this really sort of broad idea that when you boil everything down and say, why is geology happening here and not Mercury? It's because the Earth is hot. Because we have an atmosphere, heat from the sun is actually leading to all these external heat engine processes. Because the inside of the Earth is bigger than Mercury and it's hot, we have all of these geological processes, tectonic and volcanic processes. All right, so that is possibly too much of an explanation of number one here. I think a little bit later on when we get to the end of unit one and you have the opportunity to do that extra credit assignment that goes with the big test, I want to say that question one here is actually the extra credit assignment question. And then all you really want to do here is just put it into complete sentences, put it in your own words, make sure it's complete and generally factually accurate. And then you really shouldn't have any reason not to get the credit for that. Going back real quick, I forgot when I was over here to check the questions. The extra credit assignment is an essay. And I'll even just point it out in Moodle. So if you go into any of the units, but I'll just do unit one, and then go down to the bottom of unit one, there's an extra credit assignment here. It can actually be completed at any time. Okay, I'm sorry. It's not actually, I think I changed this just this semester. I think last semester I had it as the as the first of the questions. I think this is actually the last of the review questions, and it's not something we get into until lecture 5 anyway. But essentially, it's got all of the instructions here. It has to be 100 words. It has to be accurate. It needs to be grammatically correct in as far as it needs to be readable. I'm not going to not give you the points if something's one word is spelled wrong, but if everything is just really hard to read, then I might not give you the points for it. But there'll be one of these for each exam, and I find that really makes the difference in like a letter grade for people in the class. Like let's say you make like a C average on all of the exams, but you do all of these extra credit assignments. Those are the people that usually end up actually coming out with a B in the class. So definitely worth doing them and doing them all. Okay, so going back here to the review questions, the second one here is about plate boundaries and types of motion along those plate boundaries. So let's get into that one. Describe the 3 basic types of plate boundaries and their relative motion. What types of geological phenomena, again that word, form at each of these boundaries? So the basic ways that anything can really move with relation to something else is that they can move apart. That's a divergent boundary. They can move past each other. That's transform. Or they can come together, push towards each other. And those are called convergent plate boundaries. Now, all this plate motion occurs because of internal heat. And on a 3-dimensional sphere or spheroid like the Earth is, then you have all of these plates settling against each other, and they're going to move in all of these different varieties of ways, either sliding, pushing towards each other, moving away from each other. And it's at the plate boundaries where either old crust is destroyed and or new crust is created. So that's where all of the really interesting things happen geologically. So at a divergent plate boundary, the plates move apart. Often mid-ocean ridges are created. And new oceanic crust forms. I could probably make this bigger. It just occurred to me that seeing this through another screen, yeah, that's better. I bet some of these words are really, really hard to read. And if anything ever like that ever comes out, like, can you make the text bigger? Just shout it out at me. You won't hurt my feelings, I promise. So at the divergent plate boundaries, the plates move apart. What most people typically immediately jump to is if these plates are moving apart, especially if this is happening on, let's say, the bottom of the ocean, then it's going to leave this chasm into the earth. It's going to leave this deep depression on the ocean floor. And I get where that happens. I get where, people's brains are coming in with that. But you have to consider that the interior of the earth is under this tremendous pressure. And that pressure is going to boil out as soon as those plates split apart. So what happens is those plates split apart and magma comes up from below to fill in the gap and to create new rock there. And it does so in such a way that creates this lighter, more buoyant rock. And so these places where plates are splitting apart, they're actually looking more like underwater mountain ranges than they are trenches. And that's a question that's often missed on the exams is, what type of geological features would form at a divergent plate boundary? If that were multiple choice, a lot of people would pick trenches because you think divergent, split apart, you create that chasm. What's actually happening is divergent, they split apart, new rock is created, effectively underwater mountain ranges are created. And that's what these mid-ocean ridges are. So that's the basics on divergent plate boundaries. At transfer, I'll also say, why is it writing in subscript all of a sudden? I'm sorry. Maybe I'll write up here. All plate boundaries are associated with earthquakes. So this would also include divergent plate boundaries. So anytime you have all of this motion going on, either on the ocean floor, even if this motion is going on, or even especially if this motion is going on in part of the continental landmass, then this is always going to create friction. This is always going to relate to earthquakes. Divergent and transform boundaries are often more to the sort of mid to shallow focus earthquakes. The second type of plate boundary here, the transform plate boundary. What's happening down here? Okay. At transform plate boundaries, plates slide past each other. This doesn't usually create tangible geological features. So it doesn't create this thing that you can see, right? You don't get like mountains or mid-ocean ridges or volcanics, anything like that typically happening at transform plate boundaries. But you do get shallow focus earthquakes. Shallow meaning not deep, so they're closer up to the surface. Transform plate boundaries are often offsets in mid-ocean ridges, but occasionally they can be found on continental land masses too, like the San Andreas Fault. Okay, finally, at convergent plate boundaries, plates move towards each other, often ultimately destroying crust. Now, in convergent plate boundaries, you have three sort of subtypes. You have oceanic convergence, oceanic continental convergence, and then continental convergence. No. All right, I'm trying to figure out why Word decided it was spelled wrong, but it's spelled the same as it is before. Continental. I don't know. So at oceanic, and oceanic continental convergence, you have one of the two pieces of crust is always going to be older and denser, heavier essentially, and that's going to be subducted. So subduction of the older, denser plate will occur, which leads to trench formation and volcanics. Since this is all going on in the ocean, these volcanics are often island arc volcanoes. Oceanic continental convergence means oceanic crust is sinking underneath continental crust. They meet up. The oceanic crust is more dense, so it has to sink underneath the continental landmass. So again, subduction of the, in this case, oceanic crust leads to, again, usually trench formation and continental volcanics. So the west, particularly the northwest coast, is a good example of this, of an active oceanic continental convergent plate boundary. Finally, continental crust, neither plate subducts, only deformation and uplift, i.e. mountain building. And I maybe should note up here, this oceanic continental convergence will often lead to some mountain building too, because you're deforming, thickening, and uplifting the crust. So I'm sorry this kind of wound up spreading across 2 pages here. But that should pretty much sum you up here. Describing the 3 basic types of plate boundary and the relative motion. They're all related to earthquake activity. Divergent plate boundaries move apart, create new crust, create whole oceans as this continues over time. That's sort of the story of the Atlantic Ocean and the Mid-Atlantic Ridge. The mid-ocean ridges are almost always going to be uplifted parts of the ocean floor and not trenches. Transform plate boundaries, they slide past each other. You get more shallow focus earthquakes. You get deep earthquakes and convergent plate boundaries. And then they're sort of subtyped as oceanic, continental, both allowing for subduction or sinking of one of the oceanic land masses, or continental, and you get big mountains. Okay, so that basically sort of sums up the lecture 1. I wanted to come back here, see if there are any questions. Looks good so far. And that is usually sort of considered the simpler of the 2 lectures, the first 2 lectures anyway. I just considered this at the end of not just lecture 1, but a lot of the lectures, I do this sort of little field trip moment, you know, where in lecture 1, I do the Grand Canyon, in lecture 3, I think I go to a fault zone out in California. So the idea behind those is always to give you some sort of an actual real world example of one of the concepts I'm talking about in that lecture. And that's how I want you to kind of go into that material. when you get to that point, that's probably when you want to stop taking notes, put your pen down, and maybe just sort of absorb it and see how it relates to the concepts that you're already going over. I'm never going to ask specific test questions from that part of the notes or from that part of the lecture. So, when I got to the Grand Canyon part of lecture 1, the purpose of that was to talk about those two opposing forces in geology of all of these things that create uplift and all of these things that create erosion, and how the Earth's surface is this balancing point in between, because the Grand Canyon is a great example of that. So question 3 down here is actually relating to the second lecture. That one's quite a bit more challenging. I go through a couple of different types of geologic structures. Faults are just generally sort of considered the more difficult of the two. And so that's why I like to pick on faults as part of this question. But certainly if you have any questions about the types of stress, strike and dip, folds, we can definitely go through any of that as well. So unless anybody had any other questions on that, I could go through question 3 first, and then we can sort of pick apart any of the rest of that lecture that you wanted to. So the text here reads, what are the 3 major types of faults? Please describe each type of fault and include the type of stress, changes to the Earth's surface that would form as a result of movement along that fault. So basically we have sort of 1, 2, 3 types of faults. What is the stress? How does it affect the Earth? And when you get into that, I have a lot of, probably way more than 3, more like 5 or 6 names for different types of faults, but they fall into these 3 major categories. And I categorize them this way because they relate to the 3 primary types of stress. So the first of these 3 types of faults is what I would call a normal fault. I may have it listed in a separate sequence in the notes. I might have started with reverse faults, but I'll start with normal here because you want to hear about what's normal before you hear about what's abnormal, right? Normal faults aren't any more common than any of the other types of faults. I've been doing geology for 20 years and I still don't really have a good explanation for why they call them normal faults. But a normal fault is essentially a dip-slip fault. And a dip-slip fault just means that the primary motion is happening along the angle of the fault that's pointed down into the subsurface, so along the dip of the fault. So I like to think about this as a fault that would be viewed better in maybe like a canyon wall where you're actually seeing it in profile as opposed to looking down on the Earth's surface because the motion is more up-down. So a dip-slip fault, so motion angled into the subsurface and not parallel to the ground surface. A normal fault would be a dip-slip fault in which the hanging wall drops down relative to the footwall. So essentially what this means is that if there's a block of material above the fault, that's going to be this hand, and a block of material below the fault, that's going to be my lower hand down here, the upper block, or what we're calling the hanging wall, is sliding down relative to the footwall. I can even, it's something I can easily access. Once I do all 3 types of faults, I'll pull up a quick little video to show this again. But you guys have all seen this in the lecture. So in a normal fault, the hanging wall moves down. The next type of fault is going to move up. And that's the only thing that's differentiating those 2 faults. So a normal fault is a fault, a dip-slip fault, in which the hanging wall drops down relative to the footwall. In order to do that, something has to actually be pulling on both of the blocks of material. So first it has to break, and then there has to actually be motion along that break. normal faults accommodate tensional stress. It's a pulling stress, and lead to extension of the crust. So if your fault is angled and you have motion along that break, then what you're ultimately doing is pulling the Earth's crust longer. So this happens in places like the Basin and Range province. You even get this happening on more high angle faults where you have this block faulting. So block faulting is an example of normal faulting, in which you have multiple normal faults. So you have blocks of material moving up or down, depending on how those faults are angled. So this is just the first of 3 types of faults, the second being reverse faults. A reverse fault is another dip-slip fault. So again, the motion is either up or down in a dip-slip fault. In the reverse fault, it's probably going to be where the hanging wall is moving up, in which the hanging wall moves up relative to the footwall. Reverse faults accommodate the opposite of tensional stress. So a reverse fault is a fault in which you're actually pushing from either side. And when you're pushing instead of pulling, the hanging wall is instead going to move up. So I have to take my arms and actually squeeze my hands together, creating this pushing stress. And we call that pushing stress compression. And these lead to shortening of the Earth's crust. So another way of thinking of normal versus reverse faults is that they're just basically just the opposite of each other. You know, they are sort of viewed the same way. They're both sort of more visible in profile when, you know, the block is either moving up or down relative to the lower block and accommodating those 2 different types of stress. The last thing I'll say about reverse faults is that the sort of subcategory of reverse faults is the subcategory of reverse faults are called thrust faults. So thrust faults make up most reverse faults. Most reverse faults are sort of around 30 degrees. Normal faults tend to be higher angle. They tend to be closer to 60 degrees. The last type of fault has, you know, just a completely different structure. So it's not a dip-slip fault. It doesn't fall into the overarching dip-slip category that normal and reverse faults fall into. Instead of being dip-slip, these are strike-slip. And the only reason I even go into strike versus dip in a class like this with non-geology majors, non-science majors, is because it helps to understand the naming system for the faults if you know what strike and dip is. Dip is effectively the angle, like the pitch of a roof. Strike is the orientation of that roof. Maybe the ridge pole of the roof is running north-south or east-west, and then that would tell you something about the orientation of the house. And it's the same thing with rocks and faults. So this is a fault that has the actual motion along the fault along strike, and that's what's called strike slip. So a strike slip fault has motion either left or right of the strike of the fault. That's where we get into these things called left lateral or right lateral strike slip faults. It just kind of tells you which way that other block of material is moving. These are more easily viewed if you're thinking about something happening in map view and maybe some linear feature on the Earth's surface being offset. But instead of having effectively something viewed like this, where you have a top block moving down, it would be viewed a little bit more like this, where you have one block sliding past the other block. So strike slip faults have motion, has motion either left or right of the strike of the fault, accommodates the third type of stress, which is called shear stress. And can be subcategorized I knew I was going to spell that wrong, as either left or right lateral strike slip faults. So faults in particular are something where you could take these paragraphs and you could read them a half a dozen times, and it's not going to make nearly as much sense as watching either, you know, something like a video describing the three types of faults, or just to even see this displayed in pictures. So give me just a second. I'm going to track down my pictures real quick. I'm going to stop presenting, track down my pictures real quick, and then you'll be able to actually see these three types of faults. Okay. All right, found it. Restarting this. Thanks for your patience. So Spencer, I'm so sorry. I'm just seeing your question from the last last question about oceanic continental convergence. So we have oceanic, continental, which is the same as continental, oceanic. Those are interchangeable, and then continental. So
I'm sorry. I'm sorry. I meant to say continental oceanic. Is there
right?
Is that?
No, it's basically the same thing as oceanic continental. It doesn't really matter, sort of, you know, the perspective. You know, let's say you could be looking at an oceanic continental convergent plate boundary from the south or from the north, and it doesn't affect the actual processes that are going on. So they're effectively the same.
Oh, so it doesn't matter if it's oceanic continental or continental oceanic?
Yeah, it's effectively just the same thing.
Okay.
Yeah. So I wanted to show you guys, I should be sharing again, the three types of plate boundaries. So this has reverse and normal. This block over here on the left is the hanging wall, and you're not going to have images on the exam, you know, so that actually makes it quite a bit easier. So you're just always kind of considering the hanging wall is effectively just the upper block. It's the block that's above the plane of the fault. So if the hanging wall is moving up relative to the footwall, and for the purposes of this, the footwall is just standing still. If the hanging wall is moving up, that's a normal fault. If it's moving down, that's a, if the hanging wall is moving up, that's a reverse fault. If the hanging wall is moving down, that's a normal fault. Then the third type of fault has the two blocks sliding past each other. So you have, in this case over here, this would technically be a right lateral strike slip fault, because if you're looking across the line of the fault from either perspective, the other block is moving to the right. This is effectively the same thing going on over here. This is another right lateral strike slip fault that's actually offsetting this river. All of the individual faults in this picture here are all normal, just oriented in different directions, because in every single case, the hanging wall block above the plane of the fault is moving down. And so you often get in the block faulting these up-thrown and down-thrown blocks, which is where these names Horst and Graben come from. You don't need to know those terms. I believe it's German. So I just thought I'd show you that because the image often makes a whole lot more sense and makes it make a lot more, it makes it a lot easier than understanding it just purely in text. What I'm going to do, if you want the text from this, this isn't the best wording I could possibly do to answer any of these questions. But if you would like any of this text after we're done with the review session, just send me an email. I'll reply with this as an attachment. Or if you've just sort of written it out, however you want to do this to review it. It's not even necessarily, it's not even necessary per se to just have this exact wording, because you could really go through, and I encourage you to go through and really answer these in your own wording based on your own understanding of the material. So I think at this point, I'm going to go back to the meet over here and throw out, is there anything that we didn't cover as part of those review questions that was particularly tricky for you when you were watching the lectures? Anything you want to go back and talk about in more detail? If you change your mind on that, definitely send me an email. We could set up a meet and talk. I can respond to you through email. If you haven't done so already, joining the group chat, I think, is pretty beneficial. My 102 class this semester has this amazing group chat where I've just got really chatty people, so there's a lot of dialogue. There's a lot of, questions that are being answered by students before I even get to answer the questions, and they're right, they're totally correct. So I think that gives you a lot of confidence. And particularly with an online class, it's really important to still feel like you're part of a community taking this class and tackling the material together. So by all means, chat, ask any questions there. I answer them as quickly as I can. And otherwise, be in touch. Let me know if you have any concerns, and good luck on the intro test tomorrow. I'll see you guys later. You're very welcome.